For those people who want to classify stellar metamorphosis as pseudoscience, I'm sorry to disappoint you, but it's actually basic chemistry which astronomers are ignoring. It has to do with photochemical reactions, oxidation reduction reactions, changes in phases of matter, and separation of mixtures. Photochemical reactions are important. They're called mechanistic organic photochemistry. Basically has to do with light and how it causes chemical reactions. This is important for the very beginning of photosynthesis and is one of the processes during star evolution in which a star creates life. So study these processes very, very much in depth to come to full understanding of what's going on with that. Next, we have oxidation reduction reactions, or just redox reactions. It's a portmanteau of reduction and oxidation. It includes all chemical reactions in which atoms have their oxidation state changed. In general, redox reactions involve the transfer of electrons between species. Oxidation is a loss of electrons or an increase in the oxidation state by a molecule, atom, or ion, and reduction is the gain of electrons or decrease in oxidation by a molecule, atom, or ion. Oxidation reduction reactions are very, 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 very important during stellar evolution. If you just look at this page, you'll notice there is a whole lot to it, including electrochemical cells, like the galvanic cell pictured. Study these things. These are very important, and astronomers ignore them when they refer to the stars, but this is what happens. There are lots of electrochemical cells inside of a star as it evolves. Redox reactions in biology, redox reaction in industry, redox reactions in geology. Astronomers don't like talking about this because it's too much for them. And here are a lot of memory aids. These are really cool. Oil rig, I remember that one from my chemistry class back in the 2008. But look at all that. A whole bunch of stuff to study. Next, we have changes in phases of matter. Those are called phase transitions. These are also ignored by astronomers. It's a transformation of a thermodynamic system from one phase of or state of matter to another by heat transfer. In other words, entropy goes up, that's heat, goes up. If the star cools and goes down, in the side of the theory of stellar metamorphosis, the plasmatic star recombines and becomes a gaseous star, also known as a gas giant. That gas giant deposits its gas at higher temperatures and pressures, forming things like land and the core of the earth and all that good stuff, as well as liquids, which are under higher temperatures and pressures of condensation. The standard temperature and pressure only works inside of atmospheric pressure. But the pressures that I'm using for stellar metamorphosis are vastly higher. So we're going to need a completely different standard temperature and pressure to describe the interiors of stars, but more on that later. And here are all types of phase transitions. It's required to study all this stuff to completely understand it, and for people to look at this stuff to see where I'm missing things, because all this actually exists. This is not pseudoscience, but the reason why it's ignored is because they want to do weird stuff like symmetry breaking and hot early universe and quantum fields and all this nonsense. Don't look at this stuff. This is actual pseudoscience right here. The real science actually has to do with real phases of matter, like ferromagnetism, paramagnetism, absorption, crystals, transformations. All this stuff right here is interesting, and it's not cosmology pseudoscience. Basically, if you see an article where it has cosmology in there, chances are you can ignore it because it's probably nonsense. Cosmology is religion. It has nothing to do with actual measurement, and it has actually nothing to do with actual science. It's for priests only. But here we go. Ooh, phase transitions in biological systems. That's very interesting. I never heard of that before. And then you have condensed matter physics. I would be careful with condensed matter physics because theoreticians like to make things up and claim it's real when really they're just talking nonsense. So be careful when you read about that stuff. The last part of this chemistry is the separation of mixtures. This is really important. In chemistry and chemical engineering, a separation process is a method to achieve any mass transfer phenomenon that converts a mixture of substances into two or more distinct product mixtures. That's great because the Earth is comprised of those mixtures: natural gas, hydrocarbons, aluminum, which is inside a bauxite ore. You have those kind of mixtures happening, so we try to reverse those mixtures when we get those kinds of elements out of those ores. Chromatography, I'm not too sure exactly what that is, but here's a list of separation techniques. Notice how it's separation technique. During stellar evolution, it's actually combination. So basically, a lot of this is reversed during stellar evolution because the material is in its ionized form, in its gaseous form, and then it precipitates, it crystallizes, and a lot of it sublimates and deposits, which is the reverse of sublimation, deposition. Basically, you could study all of this and look into it. And if you apply chemical engineering to stars, you're much more on the fast track of understanding what happens as stars evolve than astronomers, because astronomers want to believe that stars are fusion reactors, which is very strange. Stars don't fuse matter. It's galaxies that make matter. But anyways, applying chemistry to stars is where astronomers have sincerely, royally messed up. Things like atoms, elements, compound, molecule, substance, and mixtures, moles, and the amount of the substance, phases, the bonding, the energy between the bonds, reactions, ions and salts, that's very interesting, acidity and basicity, I can't say that word, sorry, redox reactions, equilibrium, and even chemical laws. Study these things, and you'll see that a lot of this actually applies to stellar evolution. But nowhere in here will there be anything concerning stars. That's no coincidence, because they don't believe stars can have chemical reactions. They're supposedly too hot for chemical reactions to occur. But that is what the star is. It's a giant electrochemical process. Watch. Electrochemistry. This is actually very important. It actually predates thermodynamics. The study of chemical reactions which take place at the interface of electrode, usually a solid metal or a semiconductor, and an ionic conductor or electrolyte. Good thing, because plasma acts the same way as electrolytes do. It's a charged material. And if you study electrolysis and electrical current, you'll understand the stars much better. Oh, look at him, scratching his head. He looks kind of confused. He looks even more confused. I don't know what he's looking at. But anyways, these are two very important guys, Michael Faraday and Danielle. These guys are really important. Not people like Eddington or Einstein. Those guys weren't very important. These chemical guys were very, very important. You need to study what these guys do. The modern astronomers who think that space warps, that's just nonsense. People like William Nicholson and John Wilhelm Ritter and Thomas Johann Seebeck, George Ohm. These are important people. These are the people you should be researching. Walter Nernst. I can't pronounce his name. But basically, read into these kinds of reactions, and we can study how the Earth came to have the chemicals it does from earlier states of stellar evolution, back when it was a gas giant, and all the way up until when it was a very large, hot star like the Sun. Apply these kinds of understandings to the stars, and you will be leaps and bounds beyond any astronomer or astrophysicist.